Hi everyone. In this lesson we'll start off our analysis by looking at how lines behave. So a very quick example of a line would be something like this, f of x equals 4x. And we can just think of it in terms of inputs and outputs. We put in a number and we get a number 4 times bigger on the way out. So one little analogy might be, let's say you're building a fence and you have a kind of relationship between the amount of fencing you want and the cost. So let's say every foot of fencing is $4, so you put in 3 feet, the cost is 12, for example. It just kind of scales up. Now, the idea here is we can sort of intuitively think about it, but we sort of want to analyze it with sort of our calculus mentality. And so the way we do that is we think about functions like this in terms of their kind of step-by-step behavior. So one example is I imagine going to Home Depot and kind of being annoying with the clerk. So rather than just getting the whole function, I sort of walk through it and ask how it changes. So I might say, okay, how much would 1 foot of fencing be? And he says, okay, that'll be $4. How about 2 feet? $8. How about 3 feet? $12. So we basically sort of step along and sort of interrogate and see what's happening with each step. And intuitively we're doing that, but can we be a little bit more precise about what we want to do? And we can. And basically here's our procedure. We start off just with the current amount, f of x. We make a little change, which might be 1 more foot, and we call that change dx, that little piece of the input that we're changing. And then we measure the new result. So if we asked for 1 foot at first, now we're asking for 2 feet. And then we take that difference. And that's kind of the amount of the slice that we carved out, right? When we made it a little bit bigger, we carved out that little slice. And so that difference, f of x plus dx minus f of x, in this case it was 4. But we can basically have a shortcut for that where we call it df. And so this is, again, another little piece of notation. We have dx, which is sort of our little change in the input. Right? We went from 1 to 2. And then we have df, which is the change in the output, which was from 4 to 8. And so what we can do is we can actually take that ratio of the output change to the input change. And the reason we want a ratio is that it's kind of weird to talk about the whole amount. I mean, if I say, if I jumped 10, if I went up 10 feet, then it would be $40 more. If I went up 100 feet, it would be $400 more. And it's just kind of weird to talk about the whole amounts when we just sort of want to say, hey, it's $4 for every extra foot. So what we do is we say, okay, well, how much did it cost us? What was the change in cost versus the change in input? And then that's always a constant 4. So basically, we sort of want to get to that little ratio because now it's a little bit more universal, right? We're not being stuck with a specific amount. We're saying, well, okay, what was the rate at which we're increasing our cost? Because it could have jumped 10, it could have jumped 50. We don't want to talk about those differences. We want to see sort of what was the ratio right there. Now, if you notice, the derivative here, we've actually got sort of 2 different notations, right? We have this df over dx symbol, and then we also have d over dx of f of x. And what's going on? Why do we have 2 different ways to write it? Well, just think about multiplication, for example. When you learned how to multiply in school, we had kind of that x symbol, right? Like 3 times 4. And then eventually we used a dot to represent multiplication, and eventually parentheses, right? If you have x plus 4, parentheses, x plus 3, we sort of know they're meant to be multiplied. And in calculus, even a space can imply a multiplication. 2 pi r space dr, we're assuming that you want to multiply. So the idea here is that we have different notation, and it sort of draws our attention to different things. The smaller the notation, the more we're kind of aware of the things itself, and the larger the notation, the more it brings us into this mindset of, okay, we're going to be doing a multiplication here, and it's very explicit. With derivatives, it's very similar. There's a few different notations, and the style of notation that we use sort of leads our eye to different understandings. So if we use a notation like this with f prime of x, f with a dot, or d over dx of f, we're sort of still thinking about f, right? We have this shape and we're going to cut it up, and that's what we're doing. If we talk about df over dx, now we're talking about these changes. We're talking about kind of, the change our output made and the change our input made. So that style of notation actually kind of makes us think about the ratio more, and this style makes us think about the transformation of slicing it up a little bit more. And again, the reason we'd use one or the other is to sort of make a very subtle point when we're making an equation of what thing we want to think about. This is a really subtle thing. Nobody ever told me this, and there's probably many reasons why we'd use one or the other, but for me, it sort of brings my eye to different parts of the thinking process. So that's sort of my high-level understanding of why we do it. Now we can check it with the computer. What's the derivative of f of x equals 4x? Takes a derivative, and it's 4. Cool. So, we figured it out. It means that we're always getting that constant rate of 4. Basically, every input we go, we get 4 times that in the cost. Now, let's say we actually want to go backwards, and we want to go from that change back to the kind of the shape that made it. Well, we can do it, and we say, okay, we want to solve this equation here, df over dx equals 4, and we want to say, okay, well, what would have made that change? And the funny thing is we just figured it out, right? Just above, we saw that when we have, where is it? It's up here, f of x equals 4x. Once we take the derivative of that, we know that the derivative becomes 4. So if we ask, well, I had the derivative of 4, what made it? Well, we just saw that earlier it was 4x that made it. So we can kind of go backwards. We don't always need to sort of start trying to glue together pieces. We can sort of, remember in our history that, oh, okay, well, we took a derivative of something very similar. Yeah, 4x went to 4, so we just know the answer already. And if we plug it in to Wolfram alpha, it's interesting. We actually get 2 results out. So we say the integral of 4 from x equals 0 to x equals x, and solve it. Tell me what that is. And there's actually 2 answers. There's a definite integral and an indefinite integral. And this is kind of a interesting little difference, and it's kind of a subtle point. So the definite integral is when we have an integration with a set range. So we're going from 0 to x here. And we're basically trying to say, well, I have this many slices, add them up, and tell me what it is. So yeah, if you have, from 0 to x of 4, well, it'll be 4x. And another example is 0 to 13 of 4, well, we just multiply it up and we get 52. So we're just taking the actual slices and gluing them together and getting a result. Now the indefinite integral is a little bit different. We're saying, well, okay, don't just add the slices together. What was the original function that made these slices? Now that's interesting. So the original function that made it, well, we know that, oh, but it was 4x, it was $4 per foot. But it could have been something else. What about something like $10 plus $4 per foot? So let's say there's a fixed cost of 10, and then there's $4 per foot on top of that. Well, that would actually have slices of 4 as well, because the fixed $10 is there, and then every foot on top is an additional $4. So that's actually a possibility. So what the indefinite integral does is it actually figures out what is the possibilities for the original function. And what you'll see here is there's this 4x plus a constant. And the constant is basically telling you, well, yeah, it was 4x, but there was a starting point that could have been anything, really. And so you just need to take that into account. So that's sort of the difference there. One is saying, okay, here's the pieces, what do they add up to? And the other is kind of a more subtle question saying, well, no, what was actually the function that made it? Like what was the thing that actually made this set of steps that we have? And that's another subtle point that they don't often explain that well. And for me, it was a big deal. One is just kind of adding things together, getting the definite answer right here. And the indefinite one is a little bit more open, I guess, because we don't know exactly what made it, but we have an idea for the pattern that it followed. And this is building on that. We can actually go to the kind of the secret of taking integrals that we kind of figured out earlier, is that we don't actually need to solve integrals directly. We can kind of work backwards. So if someone gives you an integral and says, okay, we have df dx equals 4, integrate that and solve it. The tricky way to do it is to say, well, I remember that the derivative of 4x is 4, so I'm just going to use that. And I have this analogy about an antique stealer. So imagine that there's an antique stealer. You can bring him a broken vase, right? You have all these pieces, and he can look at it, and he'll know the original vase really quickly. He'll just look at this broken pile of pieces, says, oh, that was like a Ming Dynasty vase, and I know exactly which one it was. Now, how does he do it? Well, the easy way, I think, this is kind of the cheating way, but the easy way is actually to go in the back room, have replicas of every vase you can imagine, and start breaking them. And then you see what the piles look like, what the piles of pieces look like. So when someone brings in a pile of pieces, you say, oh, I recognize that. That is just like that vase I broke the other day, and I know which one it was. So rather than trying to put the pieces together and glue it together and try to see what it really came from, you just sort of recognize that this pile resembles this other pile that you already broke. And that's a little bit like what we do with integrals, where a lot of times we don't try to actually glue things together because it can be painful, especially if things are changing really wildly. What we do is to say, oh, well, this pile that you have here, I recognize it. We broke something else earlier and it looks exactly the same. Now, there are some things that we don't recognize. I can bring you a pile, and it's so weird and crazy that you have no idea where it came from. And in that case, we just say, I can't tell you anything. I can add up the pieces you have, and I can tell you how much they amount to, but the actual shape that made it, the equation for that shape, the original shape, I'm not sure. And so that's sort of a subtle distinction that I didn't understand either. The last step here, we can kind of learn to multiply better. Remember last time we learned that integrals are better for multiplication. So again, instead of trying to add up 2 a bunch of times, you can say, well, I just want to glue together a bunch of pieces and get the definite integral for that. I want to know the exact answer when I glue together 2, 13 times, and you get 26. Okay, the last step here is to actually make some rules. So we saw earlier that if we had 4x, the derivative was 4, and that should probably work with any constant, right? So if you have the derivative of a times x, the derivative is just a because, well, that's the change whenever you change x. And that makes sense. Then we can work backwards and get the integral and say, well, if we see a and we're integrating it up, well, the original function was ax and then plus c. That was the initial condition, right? Because it could have been $10 plus 4 or $4 plus 4 or $0 plus 4 for x. So the idea is to kind of allow for that little wiggle room where we have that plus c. So those are the kind of the key insights here. Oh, one last thing. What if we're taking the derivative of a constant? So we're not taking the derivative of 4x. We're just taking the derivative of 4. Well, what that means is we're saying, okay, I have a function where no matter what I ask it, it always returns 4. How much, if x is 1, it's 4. If x is 2, it's 4. If x is 3, it's 4. It doesn't matter. It's sort of unresponsive. And so what that means is that if it's never changing, there aren't any slices. There is no before and after, right? It's just the same amount all the time. So in that case, we say the derivative is 0, which really just means that, hey, when you try to slice it up, there is no change. When you move along, there is no change. So it's, I don't think of you don't think of a square because a square is kind of two-dimensional where you're sort of getting these slices as you go along. Just think of it as something that isn't responding at all, and you're trying to do a time lapse. You're trying to get a before and after, and it's just not changing. So that's what that intuitively means when you take the derivative of a constant. With that, I hope you understood it. If you want more details, hop into the article. Happy math.